So I'm going to talk a few minutes about modeling information with the Allotrope framework. And what you see here is a high-level diagram of the Allotrope ontologies. You can see that the ontologies, they consist of different domains. We have terms representing concepts in the area of results. There are equipments, processes, and so on. And all these very specific terms that we have in the Allotrope ontologies, they have been aligned with the top-level ontology of the Basic Formal Ontology, which is in the process of becoming an ISO standard. And this allows us to have a very precise definition of all the terms and the types in a hierarchy that strictly follows the single inheritance principle. So we can benefit from the fact that we can clearly identify the type of each information entity that we have. The Allotrope ontologies, they are one part of the story if we want to describe information. The other part that we need is the allotrope data model. So here's an example of a resulting graph structure of an allotrope data model. We have an instance of weighing. We weigh some powder, and the powder has the role of sample role. We want to weigh the mass of the powder, and the instrument that we take for the weighing is a certain balance. The outcome of the weighment is that we, for example, have some measured weight value, and we produce a trending plot, for example. So we can connect the terms here, we type them with the ontologies, and we can describe very precise context. That's the power of the ontologies and the resulting graph structure that we have. Of course, this is quite, it's a challenge to do this. If we want to be precise and have the context, then these graph structures, they will become very complex. So how do we get started? And what we have looked for is a suggestion, a way that allows us to start quickly and provide a bridge to a high-level contextualized graph model. And what we noticed is that from the data engineer's perspective, the things that we're interested in, they are usually datums. They are the serial number of the balance, for example. It's not the balance itself, it's the serial number which is about the balance. It's the sample identifier which identifies the powder. It's lots of strings, string values, identifiers, and they all share the common fact that they belong to this domain of results. Everything is information content entity, and it's then attached like this to the upper ontologies. And we can build on that. We can leverage our existing relational models that we have also in our legacy systems, for example, and start from there. That's what we suggest. And I'll show you an example how this could look like. This comes from the Virtual Materials Marketplace. This is a project which is funded by the European Union. And the point is not the details about this project. The point is here about how we applied the allotrope data format in order to describe certain high performance computing calculations. So there are people doing material modeling, and they also want to run calculations on clusters. And therefore, they have to describe somehow metadata about their calculations, what should happen there. And the system that has been chosen to manage the data is the Zonto Space system, which is based on the Open Archival Information Standard. So it's suitable for long-term archival, and it uses the allotrope data model for the description of the information. And we will now look into one example of such a high-performance computing calculation. It can be described simply by a very simple data structure. So there is this HPC job data. It has lots of fields like key values. So it's a very simple model that we have here. And the first thing to note is this is a very different thing compared to what we usually use the allotrope ontologies for. So this is not a technique in the laboratory, not HPLC or things like that. This is something very different. And we still can use the allotrope ontologies in order to model this information. And of course, it can be easily represented, for example, in a JSON structure like this. And the mapping is straightforward if we start from the fact that each of these information entities is it's a kind of information. And from the perspective of the Allotropentologies below information, there are different information concepts that we already have, for example, descriptions or facets, all these things that are then more specific kinds of information. And this mapping is really very straightforward. And we can just leverage the existing relational model that we have as the first step. If we have a look into the way that the resulting graph structure looks like, that's shown here on this slide. There we have the HPC job data, which is a yellow colored node, which represents information in the Allotrope ontologies. And it has facets, which are then the keys and values that you've seen on the slide before. And the structure, this is the pattern underlying. It's description nodes that have facets of further description nodes. And all these description nodes, then they can have values pointing to literal values. From here, the important thing to note is that that's the first start now. From here, we can extend, we can build a bridge from this description model to the fully contextualized graph model, because all these information nodes, they are about other things that they are describing from the real world. For example, we could have a look at here the operator name. It denotes a person, and this person takes part in the calculation and the execution of this HPC job. And the computer, which is doing the calculation, it has a cluster node identifier, which denotes this computer. So the allotrope graph model is just an extension of this simple approach of representing the information entities as the first start. This becomes more visible maybe if we change the layout of this diagram, if we put the process into the core, which is more in the allotrope way of modeling, that we focus on processes. If we change this diagram layout, then you see it's the same nodes as before. The job is at the center. There is a person taking part in the job. There you see the operator name. Some nodes have been added to make this alignment more clear. So operator name is a more specific kind of written name. This is coming from the information artifact ontology. Or here the HPC job name. It has also been aligned with the information artifact ontology written name. So actually this diagram, it contains a bit more information than before. And if we just focus on the information nodes themselves and just keep some written names here, remove all these identifier nodes that you have seen before, then we arrive at what I would say is the ideal knowledge graph. It follows the Alcoa principles because the information is legible. We include the written names, for example. But all the identifier nodes that you have seen before, there was the operator identifier, for example, which is still there because this one is required because of the context, that it's the identifier of the person in the context of this computer. But we don't have another identifier anymore. So the nodes themselves, they are resources in the graph model and they carry their IRIs. If we also would remove the labeling here and just focus on the actually machine required information, then this graph actually becomes more simple. And we arrive at the core of the graph structure, which would be required for processing of this graph by machines. Okay, I think I've shown that it makes sense to focus on information in the first place. And these description models, they focus on the data assets first, which are the most important pieces of our information. And they can build a bridge from the tabular models, for example, to the fully contextualized knowledge graphs with all the details. And the mapping from these models to, for example, JSON representation is very straightforward. And we also have a smart system that supports these models out of the box. Thank you. That was the short talk that I wanted to give you about the description models.
Great. Thank you, Helge.